Morning, students. Today we shall see performance analysis of half-wave rectifier, as you see the title. In our last lesson, we have seen the perform how a half-wave rectifier, a full-wave rectifier, or a bridge rectifier works. Their working principle we have studied, but we have not studied which one is good or which one is bad, and which one is good at what application rather, because as I said, all the three are good or bad mixed. We have to see the application and decide the rectifier. Today we shall see the performance analysis of half-wave rectifier. Now, in order to do that, first let us see what is a transformer. Always seen in half-wave rectifier, transformer has a single secondary winding. So it is a low cost transformer. You don't have to spend much money. Second point, transformer secondary rating, because cost of the transformer depends upon the secondary rating also. And we have always designed the transformer in such a way that the output voltage is Vm. Turns ratio has been decided in such a way. Output is Vm. So, and secondary rating is always expressed in terms of RMS. So RMS voltage of secondary is Vm by root 2. This is transformer secondary rating. Next, number of diodes. It decides the cost of the rectifier. We need only one diode, right? Next, when you go to buy the diode, they will ask you what is the PIV you want. PIV is the peak inverse voltage. You see the data manual of any diode, a peak inverse voltage is mentioned. You know. Now, what is peak inverse voltage? Let us look into this diagram here. See, when it is positive and there is a positive half cycle is applied here at the secondary, then the positive voltage goes maximum to the Vm. So at this end, it is Vm, and at this end, other end, it is connected to common, right? Similarly, when the other end becomes positive, when the other end becomes positive like this, then the diode does not conduct. And what is the maximum voltage across the diode, reverse voltage applied across the diode is Vm. This becomes Vm and this becomes 0. So peak inverse voltage, PIV. So maximum positive voltage that arrives across the diode in the reverse direction is Vm. This is a diode rating. If you want a diode with a higher PIV, you have to pay more money, right? So peak inverse voltage is always is a specification of the transformer diode of the diode. Then comes what is the output DC voltage? Output DC is the output DC waveform you see half-wave DC. So if you want to find an average of it, what you have to do? You have to integrate this sine curve over pi and then divide it, the result, by 2 pi, because during the pi to 2 pi, it does not conduct at all. So averaging will be always against 2 pi. So it is 1 by 2 pi. Here, as you see, 1 by 2 pi integration of Vm sine omega t d omega t from 0 to pi, which you integrate, it becomes Vm by pi. So remember, if Vm is the peak value of the secondary, then the average DC you get is Vm by pi. Fine. Next is What is the output RMS voltage? Now, you know how to measure RMS. RMS is the instantaneous voltage square averaged. You, you found out simple average by integrating from 0 to pi and then divided by 1 pi. Now integrate the square of Vm sine omega t d omega t. So it becomes Vm square sine square omega t d omega t, and once again averaged over 2 pi. If you do this, you will find it is Vm square by 4, and that is RMS square. This is the formula of finding out the RMS. RMS square is Vm square by 2. So Vrms is Vm by 2. Have to really remember these values. That the half-wave rectifier RMS output is Vm by 2, whereas DC is Vm by pi. So obviously DC is less than the RMS. And remaining value within the RMS is the AC content. Right? Here, what is the AC voltage is always find out this formula. RMS square equal to VAC square plus VDC square. You need not deduct and remember the value of AC because that is not much of useful, but you just remember this formula. If you can find out DC voltage, if you can find out RMS voltage, then with this formula, you can find out the AC component or non-DC component. Characteristics is a ripple frequency. Ripple frequency is, what is the ripple frequency? Look at this half-wave rectified wave. It will have a steady RMS, like if I want to draw here, it will have some steady value of RMS, average DC. And over and above this average DC, it will have some varying non-DC components. I have drawn a sine curve, but actually it is not a sine curve, but it is for drawing a sine curve, it is easy. So I have drawn a sine curve, right? And what is the ripple factor? Ripple factor is this AC component you have to find out by calculation. What is this AC component? And AC component contains infinite number of frequencies. And of course, the amplitude of higher frequencies are less. The amplitude of the lowest or fundamental frequency is highest. And we are always bothered about that only because amplitude of second, third harmonic, etc. are so low, you can forget them. So we are bothered about the first harmonic or the lowest fundamental frequency. Now, the fundamental frequency of this AC waveform is called a ripple frequency. And what is ripple factor here? Factor we are now talking about. Ripple factor is just a ratio of VAC by VDC. That means, which gives a suppose you get VDC. The purpose of the rectifier is to get DC. Suppose you get DC voltage 10 volt. But along with that, you get an AC voltage of 1 volt, which is unwanted and undesired. So the ratio is 0.1 or 10%. So ripple factor is then 0.1. And obviously, ripple factor should be always low because we do not want the AC component. Ripple factor should be always low. And what is this ripple factor? You can find out this. Ripple factor is VAC by VDC. We have seen it here, right? So ripple factor square is VAC square by VDC square. And here we got VAC square is Vrms square minus VDC square. You put this divided by VDC square. So this is Vrms square by VDC square minus 1. Now put the value of Vrms and VDC. RMS is Vm by 2, so it is Vm square by 4, and VDC is Vm by pi, so it becomes pi square by Vm square. So Vm square and Vm square gets cancelled. You have got pi square by 4 minus 1. If you calculate this is 1.21. So this is a very, very poor quality of rectifier. AC voltage to DC voltage ratio is 1.21. That means AC voltage content is 1.21 times of the DC voltage content. That means 121%. For example, if you take a numerical example, if you want a 10 volt DC, then you have to take along with that, you have to take a 12.1 volt AC. This is absolutely hopeless transformer, right? So ripple factor of this half-wave rectifier is 1.21. It is a hopeless case, you should remember. But don't lose your heart. It is not as hopeless, because later on we shall see how filters work. We shall add filters to these rectifiers. These filters are not very costly and simple design. These filters will remove the AC component, and obviously the ratio of AC to DC will enhance. So it will, I mean, without the filter, it is a hopeless rectifier, but with filter, it will become useful, right? Then we come to next point. This means that output contains 1.21 times the AC component, than the DC, which is a very, very, very poor performance, right? So far as the ripple factor is concerned, this, our half-wave rectifier, is a very poor candidate. Next we are continuing with the performance analysis. Then we have got ripple frequency. As I said, this half-wave will have a AC component. Now, you please remember your Fourier analysis, or to find out the Fourier equation or Fourier equivalent of any time domain signal. This is the, if you apply Fourier analysis or Fourier equation, then this half-wave rectifier, I have avoided here to show you the Fourier analysis, because the Fourier, then it becomes a mathematics class, right? So this half-wave rectifier, this half-wave form, its Fourier transform is like this. Multiplied by whole, 1 by pi. So Vm by pi is Vm by 2 cos omega 0 t, where omega 0 was this Vm sin omega t, that basic frequency omega 0. Then minus 2 by 3 pi cos 2 omega 0 t, plus it continues like that. So it's AC component. So this half-wave rectifier has a DC component Vm by pi, an AC component of omega 0 t, an AC component of 2 omega 0 t, an AC component of 3 omega 0 t, and continues like that. But you can see its amplitude is 1 by 2, 1.5. This amplitude is much less, 2 by 3 pi, much less. So we normally ignore the higher components. So we talk about this component, and you see its AC frequency is omega 0, F0. That means the ripple frequency of the fundamental ripple frequency, that means the frequency of the fundamental AC component in F0, which is same as the frequency of the input power supply. That means if you use this rectifier with your domestic power supply 230 volt, which is a 50 hertz AC, then the output fundamental frequency of the output will be also 50 hertz. This frequency of the fundamental AC component is known as a ripple frequency and is very important in designing the filter. Why it is so important? Because when you design a filter, your first point is which frequency you want to remove. And mind it, the lower is that frequency, the costlier is the filter. You remember this thumb rule. And higher is the frequency that you want to remove, the cheaper and easier is the filter. So this is a negative point of half wave rectifier. The ripple frequency is as low as 50 hertz. So filter design will be difficult, will be not easy. Next, we come to another component which is called form factor. Form factor is Vrms by Vdc. Like ripple factor is VAC by VDC. Similarly, form factor is Vrms by VDC. Vrms we found Vm by 2, VDC we found Vm by pi. So form factor is 1.57, right? Next is we continue to the same performance analysis. Next comes what is the efficiency? Next comes what is the efficiency? What is the efficiency of this rectifier? Efficiency of this rectifier is given by the DC power delivered to the load divided by total power delivered by the performance secondary. I am sure you have heard of this word efficiency in physics class. Efficiency of anything means suppose you have a friend who eats 1 kg of chicken every day, but he cannot do any hard work. So his efficiency is poor. Right? So efficiency of any equipment, of any engine, of any person, of anything means is the ratio of how much job he delivers divided by how much food has been given to him or how much input has been given to him. That is efficiency. Here, what is the job to be delivered? Is the DC power. So, is the ratio of DC power delivered to the load divided by the AC power delivered by the transformer secondary. Transformer secondary actually gives the AC sinusoidal AC input to the rectifier, and the rectifier passes on the DC power. So we have to find out what is the DC power delivered to the load and what is the AC power delivered by the secondary. DC power delivered to the load is, power to this resistance is V square by R, to VDC square by RL. This is the DC to the load, right? And what is the total power delivered by the transformer secondary? Transformer secondary is supplying this AC voltage, and power of this AC voltage is of course Vrms square by RL. I think these things you have already learned in your first year, electrical measurement classes. Power is V square by R. And if it is DC, you take VDC. If it is non-DC, you take RMS voltage. So power delivered to the load is VDC square by RL, and power delivered by the secondary, which is handling the full AC cycle, is Vrms square by RL. Both are V square by R. Now let us find out what is Vrms, right? Vrms we have already calculated. So so efficiency is VDC square by VRMS square, because this is RL, both side it is RL. So it is power DC divided by power RMS. So it will be VDC square by VRMS square. Putting the value of VDC and VRMS that you have already got is 40%. So efficiency of this rectifier is 40%. That means whatever AC power given to the rectifier, it supplies 40% of that in the form of a DC power to the load. If possible, we shall design a rectifier of higher efficiency, whose efficiency will be higher. Then comes another factor. This is a very important factor, transformer utilization factor. Why we bother about this? The cost of a transformer depends upon its VA rating. You might have seen in roadside electricity supply corporation transformers. It is written 400 VA transformer, 200 VA transformer. VA is voltage multiplied by ampere. VA rating. So cost of the transformer is normally related to its VA rating, right? Now we are using a transformer also, and we shall find out its VA rating. The cost of the transformer will depend upon its VA rating. And what is transformer utilization factor? Is the ratio of the DC power delivered to the load to the VA rating of the transformer, right? Suppose if you design this, consider you have to buy this transformer of 10 VA transformer, but power delivered to the load is only 4 watt. On the efficiency side, we have seen this is the efficiency is the ratio of power delivered to the load divided by power delivered by the secondary. And transformer utilization factor is the ratio of power delivered to the load divided by VA rating of the transformer. Because VA rating of the transformer is not always same as power delivered by the secondary PRMS. And since cost of the transformer is related to its VA rating, so there is another factor. And what is this factor? Let us see. RMS voltage across the secondary. This is our Vm sine omega t, this waveform. So obviously its RMS voltage is Vm by root 2. You have learned it, I think, in your school also. Vm by root 2. And what is the RMS voltage across the load? RMS voltage across the load is Vm by 2 that we have found out earlier. If RMS voltage across the load RL is Vm by 2, then RMS current through the load is Vm by 2 divided by RL, that means Vm by 2 RL. So what is Vm by 2 RL? So what is the VA rating of the transformer? VA of the transformer is the RMS voltage across the secondary Vm by root 2 multiplied by the RMS current flowing through the secondary, that is Vm by 2 RL, which is Vm square by 2 root 2 RL. And now what is transformer utilization factor? Is this DC power delivered here divided by VA rating of the transformer. So transformer utilization factor is the DC power delivered here, VDC square by RL, VDC square by RL, and this is the VA rating of the transformer. So 2 root 2 RL will go to the numerator and Vm square will come to the denominator. And VDC value also we got earlier is Vm by pi. So it is, if you put all these values, VDC is Vm by pi, so VDC square is Vm square by pi square. This RL is here, and this is 2 root 2 RL is here, and Vm square is here. If you calculate this, Vm square gets cancelled, eh? And finally, this RL and RL gets cancelled. What we have, 2 root 2 by pi square, this is 28.6%. Once again, this is pretty poor. That means if you buy a transformer of 100 VA, then this rectifier can supply only 28.6 watt DC to the load. It is less than one third, right? So these are the few parameters of uh, performance analysis of half wave rectifier. Our next lesson, we shall repeat the same analysis for full wave rectifier and bridge rectifier. And then we shall compare these three rectifiers so far as its various performance characteristics are concerned. And then you will decide which one is good, which one is bad.